Hi, everybody. I am Philip from the Department of Economics, and the paper I'll be presenting here today is called The Macroeconomy as a Random Forest. It is the latest offspring in a series of papers where we apply machine learning methods to model macroeconomic outcome. And by the way, everything I'll be saying here today, in fact, applies to pretty much any field of science where we have time series data. So I guess that's good to know upfront. Anyhow, what is so special about macro data? Well, put shortly, it is hell. So, and yes, we need to sort it out, right? Because accurate depiction of macroeconomic relationships is necessary input to good economic policies. If you want to do monetary policy or fiscal policy the right way, you need a model of how the economy is going to respond. And it turns out that getting that model from the data is hard. There are three main reasons for that. First, the interdependence between aggregates like GDP, unemployment, interest rate, and inflation are likely quite complex. And I don't think I need to convince anybody here that the economy is a complex system. So when it comes to modeling it statistically, well, the problem remains. And I just named 5 variables. It could be 500. It could be interacting in a nonlinear, dynamic, complex way. So the first big problem is that the object of modeling is complicated. Second, these relationships, they might be ever changing. So the model that we had today might not be good for tomorrow because why? The economy is constantly evolving. It also means that the data that we had from the 70s might not be good to include in our model to get an idea of where things are going to go today. So that's another big problem. And third, worse plus, the relevant historical data record is short. When you think about what made AI come to prominence in the last 10 years, it's really training these big deep learning algorithms to do speech recognition, and things like that, have self-driving cars. But all of this happened because we had millions of observations, millions of examples to train our algorithms with. Here, when it comes to US data, we have 260 quarterly observations. So that's much less than a million. So we have a complicated object to model. It might be ever changing, and we don't have so many observations to train our models on. So that's sort of an impossible situation. So how can we do better in this hostile environment? And how can we better understand what we have just modeled? So just to get things more concrete, we could think that we want to focus on something called a Phillips curve, which is a mapping that is taught in undergraduate macro classes where unemployment has an influence on inflation. Why? Because economic activity, if the economy is booming, then we expect prices to rise. And a good proxy for economic activity is unemployment. So I could want to learn this arrow mapping in my slides right there with fashionable machine learning techniques. However, like I said, macroeconomic data is quite hostile and much more than what these ML methods are usually accustomed to. So that probably not going to work too well. And even if it works well, they're black boxy in nature. So it's going to be hard to understand this mapping that we have just learned. So one thing we can do is get a little help from economics, and we're going to introduce something called betas, and it will have a subscript t, meaning that these coefficients in the linear equation will be varying through time. So really that's what I mean. What are the betas? There are time varying coefficients guiding a linear relationship. So a linear relationship is what we've seen in high school between x and y. And here, the y is inflation and the x is unemployment. And then of course, inflation, we cannot characterize it completely just with unemployment, so there is a noise component. But really the key here is that this is a linear equation, and yet it's going to be varying through time. And we have a slope at the time t, we have a slope at another time t, and then that thing changed. But when you fix t, it's a very simple problem, right? Because it just becomes at a certain point in time just a linear equation. And that's sort of nice because we took this big complex problem and now it's the sum of very simple ones, which we can have a look at to get a sense what the model is really doing. And moreover, just by telling the algorithm to put a sharper focus on unemployment, well, we nudge it in a good direction. Remember, we don't have so many observations. So we cannot really expect the algorithm to take all that data and from, 260 observation, really find out what matters and do good forecasts. So just by insisting on the small linear part here, unemployment, we make a very mild use of economic theory that nudge the algorithm into finding what really matters to model macroeconomic outcomes. So how is this going to work? How are we going to bring back the machine learning part? Well, we're going to be machine learning the beta t's rather than machine learning the outcome directly. So the traditional way would be to take all that data, put it to a black box, and then get our target. But then you only have the black box to look at. That's not so easy. And by the way, in the paper, the black box is a random forest. It's a canonical machine learning algorithm. You don't need to know what it is to understand the point of this talk, but it's just good to know it for completeness. Anyhow, what I do that is different in the paper is really I'm going to take this black box, and instead we're going to be modeling these latent coefficients that are varying through time. But these coefficients, we're going to get them, we're going to have a look at them. They have an economic meaning. And then you put it up together, and then you get back your forecast. And quite conveniently, this sort of approach to modeling time varying relationships with the machine learning method is going to mask many of the time varying patterns that economists and statisticians have proposed throughout the last decades. So does it work, right? If it didn't work, we wouldn't be here. So let's have a look at some forecasts that the new machinery has just generated. So we're going to look at the evolution of unemployment during the 2008 recession. That's unemployment change. We're going to do forecasts at horizons of 1 quarter, 2 quarters, and 4 quarters ahead. And the black line is the realized value. The yellow line is the forecast from the models that I'm proposing. As you can tell, at an horizon of 1 quarter, they're pretty much on top of one another, meaning that we have an extremely good forecast of the dynamics of unemployment during the great financial crisis. Now, the gray line is a traditional econometric model, and the green line is a traditional machine learning model. So really, we see that the yellow line is doing much better than both of them. Why? By combining elements of both of these worlds. And really, we get better forecasts by doing so. So how does that happen? Well, I said that, what's nice about the new methodology is that we can have a look at these coefficients that are time varying to get a sense where the good forecast came from. And really here in this equation to forecast unemployment, we had something called a forward-looking factors. And it's just an index of financial variables mostly that tells you where the economy is going to go next. So it's basically an index of expectations. And really what I find, by the way, the pink regions are recessions. What I find is the effect of those expectations really have a nonlinear effect, and it really changes. It depends on the state of the business cycle. So it's very weak during good times, extremely strong when we're close to a business cycle turning point, so close to enter a recession. So this gives us insights from new models on how these variables, coexist in the economy. This is the Phillips curve example. You can check it out. It's in the paper. And then just to conclude with 10 seconds that I have left, I propose a new time series model that works, is interpretable, highly versatile, is now off the shelf because there's an R package that you can download, and it can be used in any field of science as long as you have time series data. Thank you for listening.